All right, everyone. Welcome to the first ACOM seminar of the year. It's my pleasure to introduce Ann Smith, who is a senior scientist here in ACOM. Ann got her BS in physics and her PhD in geophysics at the University of Washington, and was an ASP postdoc and held research positions at CU and the University of Michigan, and has been an NCAR from 1992 to present. She's currently the chief editor of the Journal of Atmospheric Science. She's on the Saber science team, and her focus of research is on the weather and climate of the mesosphere and lower thermosphere, everything from dynamics to chemistry, with a particular focus on modeling and observations together. So without further ado, Ann, please take it away.
All right, thank you, Nick, for the introduction and for inviting me to give this presentation. I will talk about some current work on the impacts of the stratospheric variability on the global middle atmosphere. Let me see if I can make that, okay. So I'll start with some results for the mesosphere that have been seen in various publications over the last 10 years or so. So the picture on the left side shows the correlation between the winter stratosphere, and it's the temperature in the red box, and the summer upper mesosphere, which is the little black lines. And this correlation showed up because observers were noticing that the polar mesospheric clouds, which appear in the summer mesosphere in the very high altitude, seemed to vary in a way that was related to what was happening in the winter stratosphere. So this is from one of several papers. As this signal, this relationship shows up in models and in various types of observations, it seems to be fairly robust. So there was a mechanism to explain this that was originally proposed by Cornish and Becker, I think. And the idea was that you get a circulation generated by the wave activity in the winter hemisphere, but that circulation can't jump across the equator. It needs to follow this downward control principle. And so there was a mechanism to get it from the tropics or the equatorial region all the way to the summer pole by alternating between wind shear and gravity wave drag, and somehow they would feed on each other and extend this signal to the pole. I'm going to talk about a different mechanism, but first I will show you some observations. Oh, how do we change it? Okay, here are some observations from the stratosphere, and this is from our own Bill Randall from a 1993 paper. And the panel on the left shows ozone at 2 hectopascal, and the arrows indicate where there's some dynamical activity in the winter stratosphere, so alternating between the northern and southern hemispheres. And you can see some indication that when there is these periods of dynamical activity, the ozone extends a little bit into the tropics, and if you look really hard, maybe into the summer hemisphere. Bill did some analysis where, that's on the right panel. This red X is the 0 point, and the ozone tendency at that point was correlated with the ozone tendency everywhere else. And when you do this type of correlation, you can see that the signal extends well into the Southern Hemisphere, which is summer in this case. So it seems to be a similar type pattern to what I was showing in the mesosphere, where you have a signal in the winter hemisphere and it extends across. So Bill did some interpretation of this. So the left is the same figure from the previous slide. And the right panels are the meridional and the vertical velocity from the transformed Eulerian mean from a paper by Garcia, which Bill was using to interpret his results. And this is a fairly simple mechanistic model, but it showed that when there's strong wave activity forcing in the winter hemisphere, there's a poleward flow that extends well into the summer hemisphere. And then there's an equatorward flow in the mesosphere. And this is accompanied by downwelling, so similar to the downwelling that you would see in a sudden stratospheric warming in the stratosphere, and then upwelling and cooling in the mesosphere above. And the vertical velocities are strongest near the equator, but also there's some indication they extend into the summer hemisphere. So I'm going to look at this some more in both WACOM, an already published study, and then some observations using the Saber data. Okay, so here's one more case of a study, particularly in the stratosphere. There have been a number of studies looking at this. The focus has been much more on what happens in the tropics when you have strong dynamical activity. So this one is from a paper from Marta Abalos, and the wave activity is at this little pink dot, and then you can see the response downwelling in the lower stratosphere and at high latitudes, and upwelling across the tropics, and not really much indication that it extends beyond about 30 degrees. And this is from Era Interim, so it's observationally based, but not direct observations. Okay, from here, I'm going to talk about exploring this mechanism. So how far into the summer hemisphere does this response extend? And what is the time that it takes for the signal to propagate from the winter stratosphere to the summer stratosphere or mesosphere? How long do the perturbations persist? So as I mentioned, we had done some previous work with Nick Petitella and Zach Mullen from the University of Colorado to look at what was happening in WACOM. And it did show that this type of signal is seen in WACOM, and we had a very large amount of data, so 195 years, so almost 400 winter seasons to look at. And so we could apply some actual statistical analysis to look what was happening. With this large amount of data, you can actually look daily at what's happening and watch the evolution of how the atmosphere responds to impulsive forcing in the winter stratosphere. And then I will show the new results with Saber, applying some of the same analysis and looking at where it agrees with the model and where it's different. Okay, so one thing that you need to start with is some variable to quantify what's happening in the winter stratosphere. So these are self-correlations of several types of variables that people have used. So this is Southern Hemisphere, Northern Hemisphere. And the red line is EP flux divergence. So you can see after about 2 or 3 days, the correlation drops to 0. So EP flux divergence there's no memory. As soon as something happens, there's an impulsive forcing on the atmosphere, and that forcing can disappear very quickly. And this is from MERA 2 reanalysis. Whereas temperature from both the Southern Hemisphere and the Northern Hemisphere has a very long memory. This shows out to 15 days, and what happens in the stratosphere is still correlated with the temperature 15 days away from there. Zonal wind is quite similar to temperature. So in the analysis, everything that follows, including WACOM and Saber, the EP flux divergence is used for the index of this stratospheric dynamical activity. And I have to remind you, EP flux divergence is negative for strong winter activity. So the signs of the correlations aren't always what you expect. So when there's strong wave activity, it's negative. And if you have a positive temperature response, then you will have a negative correlation, even though you expect a positive temperature response. I hope that doesn't confuse anybody, but anyway, that's what you're going to see. Okay, now here are some results from WACOM just showing you what happens. So this is correlating that the region that was picked is around 65 degrees north and 1 hectopascal averaged over an area. Have daily data from December to February. And as I mentioned, there are 165 years, sorry. Seasonal cycle has been removed. So the correlations are correlations with the wave activity. And these different panels are a lag. So I drew a little red dashed line around 0 lag. So this is when there's the daily correlation, the same day EP flux divergence in the winter and the temperature response everywhere. So negative lag means what the temperature is doing ahead of a signal in the EP flux divergence. And you can see there's not much of a signal. And then starting at the time of the 0 lag, so simultaneous, a signal develops where it's associated with downwelling in the high latitude stratosphere, upwelling high latitude mesosphere, and then the opposite sign elsewhere. And the maximum maximum values for the correlations for temperature occur about 2 days later. Yeah, 1, 2, 3 days lag have the maximum response in the temperature. Okay, so the other thing to note here is that the whole pattern is instantaneous. As soon as it shows up in the high latitude winter, it shows up everywhere at the same time. And then it tends to decay away very slowly, you can see, but more or less in phase. So it's a very fast global signal. If you look at the same thing for the Southern Hemisphere winter, the pattern is actually quite similar, except the magnitudes of the correlation coefficients are smaller. But again, you see a pattern that extends well into the Summer Hemisphere and then persists for some days. And remember, the wave forcing itself doesn't persist. It has a self-correlation timescale of just a couple of days, and then it goes away. Okay. So the first thing that we looked at with the WACOM results was to see whether the wave activity in the Summer Hemisphere plays a role, as per the explanation for what had been happening in the observations. So in the Winter Hemisphere, I think there has always been agreement about what's happening, the mid to high latitudes. The planetary wave dissipation leads to poleward flow in the stratosphere. There's an associated downwelling and warming in the high latitude stratosphere, and there's upwelling and also some changes due to gravity wave interactions in the high latitude mesosphere. So you get warming in the stratosphere and cooling in the mesosphere. In the tropics and the summer hemisphere, the momentum balance and continuity, as per the results from the simple Garcia model that I showed earlier, give a simultaneous response in the tropics and into the summer hemisphere here. And the flow towards the winter pole extends all the way. And then there's upwelling and cooling in the stratosphere and downwelling and heating in the mesosphere. The planetary wave activity is weak, so we wouldn't expect that to play much of a role in this process, but gravity waves might contribute as per the theory of Cornish and Becker. So this is looking at it in some more detail. The left column, shows the same results I showed before, but just for a few different lags. 0 lag and then +3 days. So 3 days following the wave activity and 6 days following. And the temperature, as before, the temperature perturbations extend well into the summer hemisphere. This is the transformed Eulerian meridional wind. And you can see that shows up very quickly right at the 0 lag time. And then after a few days, close to a week, it is disappeared quite a bit, even though the temperature perturbations still persist. The resolved waves are very strong in the winter, very strongly correlated with the EP flux divergence. And it should be a correlation of 1 right here, where the resolved waves are being correlated with itself. But barely any indication that anything is happening in the summer hemisphere, stratosphere, or mesosphere. And likewise, for the gravity wave drag, there's some indication of a response into the summer mesosphere, but not right at the beginning. The response in gravity waves comes a little bit later than the response in the circulation, which is almost instantaneous. So the WACOM results indicate that there's a very rapid and short-lived response in the circulation, and that is associated with the response of the temperature in this summer stratosphere and the summer mesosphere. So we put this all. Okay, sorry about the interruption. This is one variable that's trying to capture everything that's happening in the summer hemisphere based on the correlations that I showed before. And it shows that there's a rapid response. This magenta color and the blue color are the two components of the mean meridional circulation. A rapid response that disappears very quickly. There's a temperature response that shows up a couple of days later and has a very long tail. And there's almost nothing happening with the waves in the summer hemisphere. So this just a summary that WACOM simulations are very consistent with a global circulation induced by the wave activity in the winter stratosphere, and that waves in the summer stratosphere are not playing a role. Okay, so I need to go backwards. How do I do this? I can't, let me see if I can figure out. Sorry, I keep.
You can use the back arrow on your keyboard.
Okay, all right. Sorry. Okay, so that's it for the WACOM results. And now I'm going to show some Saber observations trying to look pretty much the same thing. So winter, Northern Hemisphere winter, 3 months of data. And then the season for the Summer Hemisphere is even a little longer because it encompasses a longer period of strong wave activity. Because of Saber sampling, I couldn't get the EP flux divergence from Saber in a continuous time series. So that is calculated from MERA 2, and it's at the upper stratosphere in the winter hemisphere, just as from WACOM. And unfortunately, there's not as much data, but there's more than a little bit. So there are 18 complete Northern Hemisphere winters and 19 complete Southern Hemisphere winters. And that's what's going to be looked at. Okay, so Saber, probably many of you are familiar with it. It's an infrared instrument on the Time satellite. Was launched in 2001, is still operating well. It precesses, so it covers 23 hours of local time. And the sampling is a problem. So it extends at any given time from 53 degrees in one hemisphere to 82 degrees in the other. So there's not a continuous data set in the high latitudes. But everything from 53 south to 53 north is sampled continuously. And I'm just going to focus on that. I won't look too much at, or I won't look at all in this presentation at higher latitudes. So we'll look at temperature, ozone, water, and also local time of temperature. Okay. So here's the same analysis. This is Northern Hemisphere winter. Again, there's a red dashed line around the 0 lag. This is -7-day lag to +8-day, and the correlations of the temperature with the wave activity. And unfortunately, you can't see what's happening in the high latitudes of either hemisphere because of the Saber sampling. But you can see that in the tropics and in the Summer Hemisphere, there's a strong correlation, and it looks quite similar to what we were seeing before in the WACOM analysis. And in the mesosphere, it's noisier, and there are some differences, which I will show you just now. So this is just taking one of those panels. It happens to be 5-day following wave activity. And the WACOM panel is on the right. I blocked out the parts where there's no overlap with Saber. So in the stratosphere, it looks very similar. The magnitude and structure, the place where it switches from positive to negative it's quite similar, and even a little bit into the lower mesosphere, but the upper mesosphere looks different. This pattern in the highest part of the Saber analysis, to me, seems similar to what you might expect if you were seeing something in a diurnal tide. So I'll get back to that later. So mainly the thing that shows up from this panel is that the temperatures are similar to what we saw in the analysis up to about 70 kilometers or so, and then they're different. Okay, we did the same thing for the Southern Hemisphere, and similar to what was seen in WACOM, the correlation coefficients are weaker, but you do see this same kind of pattern extending into the summer as far towards the summer pole as we have reliable or continuous data from Saber. And things are noisy, particularly in the mesosphere, all of the mesosphere. And this thing that I was wondering if it was a tidal pattern doesn't really show up very well. I also just point out here, and it's true for all of the results I've been showing, So the analysis doesn't have any smoothing in time. So the atmosphere has smoothing in time, but the actual analysis doesn't. So the data used for each of these panels is completely independent. So if you see something that seems to continue day after day, it's likely that it's a real signal. Okay. So what would you have for trace species? Well, there's two different ways that trace species and temperature perturbations could be related. One is if transport is dominant, in which case the change in, here I worked it up for ozone, but the perturbation to ozone would be in phase with temperature perturbation when ozone mixing ratio is increasing with altitude. And it would be the opposite sign of the temperature perturbation when the ozone mixing ratio is decreasing. If it's photochemistry dominated, for ozone, it's because the chemical loss increases with increasing temperature. So it will be a negative relationship, that the ozone response will have the opposite sign as the temperature response. So for ozone, you expect transport in the very lowest part of the stratosphere, and so and into maybe the middle stratosphere, and then photochemistry takes over. And the upper part of the mesosphere, I won't get into the chemistry for that part, but atomic oxygen transport is actually what will determine the ozone relationship to the temperature, the perturbation relationship. Okay, I'm also going to look at water, and there I expect that transport would be the thing dominating the water response to this type of circulation everywhere. Okay, so here's the ozone. In the lowermost part of the stratosphere, well, even up to about 10 hectopascal, you expect that ozone perturbations will be in phase with temperature perturbations. And then due to either transport in part of the stratosphere and then photochemistry all the way through much of the mesosphere, you expect ozone perturbations to be out of phase with temperature perturbations, and then something different in the upper mesosphere. And actually, the responses do look pretty consistent. So you have this small region, weak signal of ozone positive response in the lower stratosphere. This is quite weak. And then mostly you see a negative response. So this is actually a positive ozone for high wave activity, because as I mentioned, the sign is negative for high wave activity. And it's the opposite sign as the temperature. Nothing much happening in the mesosphere. There's not much ozone there, except you see in the upper mesosphere, this may be a transport signal due to atomic oxygen. It's not a real strong correlation, but it seems to persist. So ozone sort of behaves as one would expect. The same in the Southern Hemisphere winter, although the signal is fairly weak and not much at all in the mesosphere. But all of these positive lags indicate that the ozone perturbation extends as far into the Summer Hemisphere as we have continuous observations. Okay, now water, a little bit different here. Here's what the water looks like from Saber during Northern Hemisphere winter. So if it's transport, you would expect that the water perturbations would be in phase with the temperature perturbations up until about the stratopause, and then above there, the water perturbations would be out of phase with the temperature perturbations. Okay, and the water signals are not very big, but they do have some consistencies. In the summer, mid and upper stratosphere, you see this positive signal where you had a positive signal in the temperature. So this fits with the perturbations that just below the maximum in water, if you have a positive temperature signal, you will have a positive signal perturbation in water. And there's also an indication in the upper mesosphere that the water changes due to dynamical activity, and then it persists. This seems to be related to high dynamical activity, which is a negative, brings down water in the tropics with very, very dry, and there's no way to reform it. And so this positive indication means this water signal is very, very dry in the tropics and a little bit into the winter hemisphere. The thing that's puzzling here is in the lower half of the stratosphere. This is not consistent with vertical transport. This is a weak correlation, but it lasts for more than a week. Out of phase with the temperature correlation. So it's not due to vertical transport. I don't know if it's meridional transport, if there's some other processes that have a time scale that would overrule what's happening for vertical transport. There's not very high water gradients either in the vertical or the meridional direction here. So I'm sorry to tell you, but I don't know what's happening there. Okay, so one of the questions is how and why do the signals persist? I already showed earlier that the wave forcing does not persist. It's a rapid and rapidly disappearing, at least from the WACOM results. The circulation that's driven by that wave forcing also appears rapidly and disappears quite rapidly. So here's just looking at the persistence by looking at lags, and this goes way further into the future than what I had shown before. So the left column is temperature, 2-day lag, so you get a strong response in the temperature that extends as far to the summer pole as we can do the analysis. 8-day lag, there's still a fair temperature signal. 16-day lag, there's still a signal in the temperature, which it is now mostly in the lower part of the stratosphere. And unfortunately, we can't see into the winter stratosphere. I think maybe people are aware, at least for major events like sudden warmings, often the lower part of the stratosphere will stay in a warmer regime for quite a long period of time, weeks or more. And here, even 24-day lag for the temperature, you still see some indication of a signal in the lower part of the stratosphere extending quite toward the mid-latitudes in the summer. That is there. Everything else has gotten a bit noisy, but the signal seems to last in the summer of the temperature. For ozone, a strong signal after a few days. After about a week, you still see an indication of that signal. Anything after that is quite noisy, and I wouldn't claim that there's anything that you can see here. There is some consistency from day to day, but the signal being quite noisy in the vertical and in the meridional direction. So it looks like the ozone that responds to either transport or to photochemically to the temperature perturbations does not persist even when the temperature perturbations are there. For the water vapor, the main thing that I can see from here is that this positive signal, which is very dry air in the tropics and into the winter hemisphere, persists for weeks after a dynamical event. So I think that makes sense in terms of what you would expect water to do. Okay, now I wanted to go back to this question of whether there's a tidal signal. So let's look here. Okay, so the timed satellite that Saber is on is precessing, so you can get some information about the diurnal tide, but it's a slow precession. On any given day, you can only measure 2 local times, one in the ascending orbit over and over again at all the different longitudes, but the same local time, and one in the descending orbit, same thing. So this is taking, on the left panel, all of the temperature observations for all the years for December, January, February. And this is plotted against local time and pressure, so in the upper mesosphere. So these stripes that you see, diagonal stripes going down, are the diurnal tide. And, you know, it's a big signal up there, so plus or minus 20 Kelvin, and this is not even the season with the highest magnitude. Okay, and these variations, instead of being completely continuous, all the same magnitude, these variations could be due to different times where different local times were observed. It could be due to fewer observations at certain local times. You can see right at noon, there's never any observations. But basically, there's a strong tidal signal. Now, this is the equator where this is shown, but this pattern of opposite sign at the equator and about 30 degrees north and south, and then changing sign with pressure, looks like a signal that you would see for the diurnal tide. So let's try to look a little bit more and see if this is a tidal response. Okay, so this is taking the left panel, nighttime. This is just for one lag, 5-day lag, just to illustrate. This is all the nighttime temperature perturbations. So temperature perturbations are in the up and down, and perturbations in the wave forcing, the index that's used for all the analysis I've shown, are in the left, right. And you don't see a real strong correlation. And to the extent that there's any correlation at all, it's in this little quadrant here where very strong negative perturbation, del F, is associated with negative temperature perturbations. But since the signal persists for a week or so without changing the way it looks, we can combine to get more local times to fill in this grid. We can combine the signals from different lags. And this is what the tide looks like. You can see it's quite a bit noisier than what I showed before. So this is using only temperatures when the wave forcing is strongly negative. And then the one below, the middle panel on the right, is only temperatures where the wave forcing is more positive. So really where nothing is happening, or it's recovering from a wave event. And even though both of these are quite noisy, if you take the difference, it does have this same kind of tidal shape of a downward propagating phase. So maybe it's tidal, I don't know. If you take the amplitude of these two, so if you can just fit a curve to the temperatures and get an amplitude of how big this wave is. And the amplitudes are different. This is about 2 Kelvin different. So when the wave forcing is stronger, or in the period following stronger wave forcing, the amplitude of the tide is smaller than it is at other times at the opposite extreme. And there's a little bit of a phase shift. This is it gets up to about 2 hours or more difference in the phase of the tide. So the problem is, because of all the issues of trying to get tides from an orbiting satellite, and the fact that you can only look at one local time or 2 local times at any given time, it still needs to try to figure out how to isolate whether this is a real tidal response or it's the result of the aliasing. So the verdict is out on this, but there's definitely some signal that shows up. And then the question is whether it's real or not. Okay, so I am going to give you a summary of what I said. So analysis of Saber for 18 northern winters and 19 southern winters shows a correlation between the wave forcing in the winter stratosphere and the temperature throughout the global middle atmosphere, all the way through the stratosphere, all the way through the mesosphere. The temperature perturbations at some levels, levels in the Southern Hemisphere persist for several weeks after the wave forcing subsides. Particularly, it's most persistent in the lower stratosphere and in the middle mesosphere. The response in the tropical upper mesosphere indicates shifts in the amplitude and phase of the diurnal tide following stratospheric wave forcing. The persistence of the tide response suggests it's associated with global temperature response and not the wave forcing. What I mean there, the wave forcing is impulsive and goes away quickly, but the tidal response persists for a week or more. So it has to do with something else that responded to the wave, or to the tide itself having some memory, but not to the directly just to the wave forcing. And correlations of ozone with wave activity are consistent with those of temperature, indicating higher ozone with lower temperature, except in the lower stratosphere and the upper mesosphere, where there's a transport signal that has the opposite sign. Persistence in the ozone and the water perturbations could be due to their dependence on temperature. So the temperature persists, and therefore if the perturbation in ozone is depending on the temperature rather than the transport, it will persist also. Or if the ozone and water have responded to the transport, they could persist because the photochemical lifetime is slow. So, okay, that's what I had to say. I can take questions.
Okay. So yeah, if you have questions, please submit them through Slido. While we're waiting, I have a question. So this sort of persistence of the anomalies after the like you said, the impulsive wave forcing. Can you say something then about sudden warmings where you have a rapid series of large pulses of wave energy? Like, should you actually start seeing that as I guess, one way to interpret it is a local sort of dynamical process, sort of vortex stripping and things, but there must also then be a sort of hemispheric situation where I'm just thinking the hemisphere starts to accumulate this sort of forcing from the waves over the period of, say, a week or two. So I don't know if that helps, but can you interpret like an SSW then through this kind of persistence framework, like how it impacts the whole system?
Okay, I'm not quite sure I understand the question, but so
Sure.
the temperature persists after the circulation goes away. That seems to be what happens in WACOM, and since everything else looks similar to Saber, I'm extrapolating a bit, but assuming that that's what happens in the atmosphere as well.
Sure. I guess what I'm saying is, my interpretation then is if you have a period of, say, 2 weeks of heavy wave forcing on, say, the vortex, you know, should you be looking further afield for the processes that lead to the sort of cascading dynamics of a sudden warming if the whole hemisphere is accumulating this sort of persistent anomalies? Like you have a wave event, you propagate around some temperature anomalies, which imply some angular momentum anomalies. You keep doing that. Eventually, you're changing the whole circulation of the stratosphere. So I'm just wondering if, you know, I don't have a direct question. I'm just trying to understand, like, if I think of this sort of persistence pathway, can I just keep adding up over time, like the effect of the wave forcing, and think of it as some sort of linear process then? Because if you keep hitting the forcing faster than the anomalies that are persisting can dissipate, eventually you're changing things far further afield from the vortex during a sudden warming.
Right. I don't know how, since all this analysis is based on correlations in time. So things that go up and down, you'll see more than you would something that's persistent. So I think it takes maybe a different look at the results to see.
Got it.
Okay, I see there's a question from Dan. The answer is yes. The question, I don't know if everybody can see the question. Did you look just within a Saber yaw period to investigate the response at higher latitudes? Well, yes, in combining all the different observations that appeared during the 3-month period. And the temperature response looks exactly like what you would expect and like the WACOM results. The ozone and the water were so noisy. And for all of them, there's a discontinuity in the analysis when you you're comparing some results that have data every day and some results that only have data half the days. And there's a discontinuity between them. I thought it made the plots very noisy. The signal in the Summer Hemisphere is pretty small also. So that's why it's not shown in any of the plots. But if you wanted to see it, we can talk later and I can show you what I found. Okay, another question, Bill. Okay, it looks like the different temperature response times are consistent with the radiative damping time. Time scale, long, right. Yeah, I think that must be the reason. And for the constituents, the chemical relaxation time scale. I thought you might be making your way toward the polar summer mesopause. Any comments? I'm not sure. Yeah, it was. Okay, sorry, I'm not sure what this question means. If you want to put some more in the Slido, then I can try. I could try to answer it. Okay, there's a question from Ramesh. I'm just curious to know how the water vapor varies in radiative damping time scale. I thought you might be making your way towards the, oh, that's part of Bill's comment. Okay, sorry, I'm getting the questions mixed up. Just curious to know how the water vapor varies in response to temperature in lower and upper mesosphere, whether transport of photochemistry or photodissociation. So the photodissociation should not have much of any response, a relationship to temperature. I think the water response should be transport. That's why I was confused about what's happening in the stratosphere in the subtropics and mid latitudes of the winter hemisphere. Okay, any more questions? Okay, Bill, if you can ask me this question again, I can try to answer, but sorry, I don't know what you mean.
We can wait for a second.
Okay.
Actually, I might have missed this. This should be a quick question as opposed to my non-question earlier. I may have missed this, but is there a good idea of why the correlations are so much more stronger and robust in WACOM versus Saber, even granting a longer sampling period? Is it just, is the variability too smooth in WACOM?
Could be, yeah. So Saber's noisier and yeah, it's a lot shorter period, which you mentioned, noisier, and it may be that, you know, that there's a lot of other things that could be happening in the atmosphere, and WACOM may be missing some of them. But I thought they were remarkably similar, just not as clean as you would get in the model. Okay, from Dan. Oh, no, here, before that, Cora. Back to Bill's question, I think. What are the implications of your results for the effects of sudden stochastic warming on polar mesospheric clouds? I think the signal is real, it's robust, and it is not associated with gravity waves. It's just the circulation. So I don't know if that answers your question. We discussed it some in the 2019 paper. Looking back at the observations, most of them aren't all the way at the pole, and they are seem to be consistent. Most of the studies use the temperature perturbations instead of the wave activity. So you can look at monthly means and still come up with a signal. So our interpretation from this was that it's a global circulation that's causing this correlation, and that the correlation is real. Okay, I hope that answered that. I see from Dan again, I see Nick as your co-author. Any plans to look at cosmic data? I haven't made any plans to look at it, but thanks for the suggestion. I'll talk to Nick about what the options are. Okay, Bill, yeah, sorry, okay. From John, does the difference in disturbance lifetimes, much more rapid dissipation of winds than temperatures, indicate a large Prandtl number for the atmosphere? So it's the circulation that disappears, and the zonal wind is probably, well, it has to be have the same kind of time scale as temperature, because the temperature and the zonal wind have to stay within some kind of balance, like a thermal wind balance. For a large Prandtl number, I don't know. I think of the Prandtl number in terms of gravity waves, and the gravity waves don't really have too much to do with this. So I would have to think about how that could have some impact on the circulation. Sorry, I don't have an answer for you on that. Okay.
All right. looks like that's it. So thank you, Anne. We appreciate you giving this seminar, and everyone else, we will see you in, let me check really quickly, I think 2 weeks for our next one. Yes, 2 weeks from now. So bye, everyone. See you later. Thanks, Anne.
Thanks for coming. Bye.